We are continuing with the question 66. So this is question 66. Voltage across the capacitor as shown in the figure is expressed as Vc of t is equal to A1 sin omega 1 t minus theta 1 plus A2 sin omega 2 t minus theta 2. So this is the figure that is given. Here we can see that this is 20 sin 10 t and here this is 10 sin 5 t. The values of A1 and A2 respectively are to be founded. So this is A1 and this is A2. So we will have to make a similar equation in the same format as Vc of t is given. Okay. And once we make similar equations, then it will be easy for us to compare the equations and find out the values of A1 and A2. So this is the figure that is given. So we will have to make a equation for Vc of t. Here in this problem, even though this is a Kirchhoff's KCL KVL problem, we are going to apply superposition theorem because we are having two different sources. One is a current source and another one is an voltage source. So we are going to apply superposition theorem. As the step 1 of applying superposition theorem, we are considering voltage source. That means 20 sin 10t alone. So we are first considering the voltage source only. Voltage source is 20 sin 10t. So when considering voltage source, we will open circuit the current source. So now this is the figure considering only the voltage source, and we have to find out the value of Vc1 of t. What is Vc1 of t? Vc1 of t is actually voltage division. So that means 20 sin 10t into minus j.1 divided by 1 plus j minus j.1. Will give you Vc1 of t, and simplifying it approximately you will get Vc1 of t as 2 sin 10t minus 84.28 degree. So let us put it as equation number 1. Now considering the current source only. So when we are considering the current source, what happens to the voltage source? We will be short circuiting the voltage source. So we are considering the current source 10 sin 5t alone, and we are short circuiting the voltage source, and we are going to find out the expression for Vc2 of t. Vc2 of t is actually the node voltage. So we are going to write the equation for the node. So it is Vc2 divided by 1 plus Vc2 divided by minus j.2 minus 10 sin 5t is equal to 0. From this we will be able to isolate Vc2 of t as 10 sin 5t divided by 1 plus j5. So from this we can write Vc2 of t as 1 point, because we have to do this division operation. Then Vc2 of t can be written to be 1.97 sin 5t minus 78.69, and this is put as equation number 2. Now we have did this problem so far with the superposition theorem. So what will be the total voltage according to superposition theorem? It is the algebraic sum of case 1 plus algebraic sum of case 2. So we are going to sum this up, and then we will get a Vc of t expression as expression 3, and there is a given equation of Vc of t. The Vc of t equation is A1 sin omega 1 t minus theta 1 plus A2 sin omega 2 t minus theta 2. And rewriting that equation and comparing the obtained equation with the given equation, we will be able to isolate A1 and A2. So what is A1 here? A1 is 2 in the first term, and A2 is 1.97, which is the coefficient of the second term. So what is our A? A becomes 2 and B becomes 1.97, approximated to be 1.98. So that is what is our closest answer is. So what is our answer? Our answer, we will go for 2 and 1.98, which is option A. So this is a 2-mark question from 2014 GATE examination. Now moving into the next question, question number 67. The total power dissipated in the circuit shown in the figure is 1 kW. So here is the load. So this is the load with R and XL, and they are saying that the total power dissipated in the circuit shown in the figure is 1 kW. The voltmeter across the load reads 200 volt. Value of XL is what is the question. So the load is R plus JXL. So we will have to find out the value of XL, because the voltmeter is reading 200 volt when it is connected across the load, and this is the voltmeter. Okay, it reads 200 volt. So we are going to draw the figure again. So this is our figure. We have an AC source and there is a resistance capacitance combination and another capacitance in parallel with the arrangement. So given the total power dissipated in the circuit is 1 kW. So that means 1000 watt is the total power that is dissipated. So how the power is dissipated? The power is dissipated as I square R. I square R. So we are having a 1 ohm resistance here. Okay, and the 1 ohm resistance is carrying 2 amperes, and then there is R which carries 10 amperes. Okay, so that will be our total power dissipation. We will not be considering the capacitance or the inductance for considering the total power dissipation. So it is actually 2 square into 1 plus 10 square into R, which contributes to 1000, from which we will be able to find out the value of R as 9.98 ohm. So voltage drop across R. So when a 10 ampere is flowing through R and we have obtained the value of R. So when R is 9.98 ohm, what will be the drop across R? Drop across R will be 99.8 volt. Okay, because it is 9.98 into 10. So it becomes 99.8 volt, which is the drop across R. Now it is already given that the drop across the load is 200 volt. Okay, but we obtain that the drop across resistance is only 99.8 volt. So we will have to find out the drop across XL. So what is 200 volt? It is VR square plus VXL square the whole root. So in that we can substitute VR square, and then from the expression we can reverse the expression to VXL equals root of V square minus VR square. V is 200, VR is 99.8. From this VXL we will get it as 173.32 volt. Now VXL is equal to I into XL, or XL is equal to VXL divided by I. What is I? I is 10 ampere that is flowing through the R and XL. The load carries a current of 10 amperes. So it is 173.32 divided by 10, which will come to 17.332 ohm. So what is our answer? Our answer is XL. What is our question? The question is the voltmeter across the load reads 200 volt. The value of XL is what is the question. Now what is the value of our XL? Our XL is of value 17.332. So what is XL? XL is 17.332. That is our answer. So that is about question number 67. Now moving into question number 68. The line A to neutral voltage is 10 angle 15 degree volt for a balanced 3-phase star connected load with a phase sequence ABC. The voltage of line B with respect to line A is given by. Okay, so we are having a balanced 3-phase star connected load with a phase sequence ABC, and a neutral voltage of A is given. So we are having a balanced ABC arrangement, and this is the phasor diagram. Given that the neutral voltage VAN equals 10 angle 15 degree. 10 angle 15 degree. It is a system of balanced system. It's a balanced system. So when our base is 15 degree ahead, we will have to consider every other phasor plus 15 degree. So normally it will be 10 angle 0, 10 angle 120 degree, and then 10 angle to 40 degree. But since our reference is 15 degree advanced, we will have to take it as 10 angle 15 degree, 10 angle 135 degree, and 10 angle 255 degrees. So that is our VAN, and VBN, VBN and VCN. So these are the three voltages: VAN, VBN and VCN. So what we have to find out? We have to find out the voltage of the line B with respect to line A. That is what is to be found out. So the voltage of the line B with respect to A. Voltage of the line B with respect to line A. So we will have to find the voltage of the, so there is a correction in the question. We will have to find the voltage of line B with respect to line C. Okay, with respect to line C. So there is a small correction in the question. It is not B with respect to A, it is actually B with respect to C. So to find B with respect to C, we want to find out VBC, which is VBN minus VCN. We already know what is VBN. VBN and VCN we already know. So what is VBC? It is VBN minus VCN. So substituting the values of VBN and VCN, we will get VBC to be 10 root 3 angle minus 75 degree volt. So that is VBC with respect to B and C. We have obtained VBC with respect to the voltages VBN and VCN. So it is 10 root 3 angle minus 75 degree. So what is our option? Our option is option C, which is 10 root 3 angle minus 75 degree volt. So that is about question number 68. Now moving into question number 67. This is a 2014 question for 2 marks. The power delivered by the current source in the figure. So the current source is a 2 ampere source, and we will have to find out the power delivered by the current source in the figure. So to find the power delivered by the current source, we are recreating the figure and we are applying node analysis at V1. Then it becomes V1 minus V1. V1 applying node at P. So we are going to apply node at P. So this we will be taking to be node P. Okay. So then the voltage will be VP, isn't it? Voltage will be VP. So VP minus V1 divided by 1 plus VP minus V2 divided by 1 minus 2. So I will be just slightly modifying this equation as VP minus V1 divided by 1 plus VP minus V2. VP minus V2 divided by 1 minus 2, because 2 is the incoming current. Minus 2 is equal to 0. From this, the equation we will be getting it as, you will have to solve this equation because I have modified this equation. So this is the fundamental basic equation, and this fundamental basic equation you will have to find out the value of, you will have to substitute and make an expression in this form. Okay, so 2 plus V1 plus V2 divided by 2. Also, it is given that V1 minus V2, the voltage difference between V1 and V2 is 1 volt. Okay, so V1 minus V2 we can substitute to be 1 volt. Okay, and V1 is equal to 1 volt. What is the value of V1? V1 with respect to 1 is with respect to ground is 1 volt. So substituting V1 is equal to 1, we will get V2 is equal to 0 volts. Okay, so we are getting V1 is equal to 1 and V2 is equal to 0. So V1 is equal to 1 and V2 is equal to 0. So you have to put these values of V1 and V2 into this equation. So here it becomes 1 plus 0. Okay, because V1 is equal to 1 and V2 is equal to 0. So it becomes 3 divided by 2. Okay, so it is 3 by 2 volt. It is 3 by 2 volt. Now the power delivered by the current source is actually V into I. So that is the power delivered by the current source. The power is delivered by the current source to the point P. So the power delivered by the current source is V into I. What is our V? V is equal to 3 by 2. And what is our I? I value is equal to 2 amperes. So V into I becomes equal to 3 watts. It becomes equal to 3 watts. Because I is equal to 2 ampere, that is given with the source. So that is the answer for this question. Now moving into question number 70. The voltage is developed across the 3 ohm and 2 ohm resistors shown in the figure are 6 volt and 2 volt respectively. The voltage is developed across the 3 ohm and 2 ohm. The 3 ohm and 2 ohm resistors. Voltage is developed across the 3 ohm and 2 ohm resistors shown in the figure are 6 volt and 2 volt respectively. With the polarity as marked, what is the power delivered by the 5 volt voltage source? So we will have to find out the power delivered by the 5 volt voltage source. On the left hand side we will take the arrangement to be network N1, and on the right hand side we will take the arrangement to be network N2. So from this we are going to find out the power delivered by the 5 volt source. So this is our arrangement. This is our arrangement. There is a 5 volt, there is a 6 volt and a 2 volt across 3 ohm and a 2 ohm. So we will have to find out the value of power. So what is power delivered? What is the power delivered by the 5 volt source? So we will have to find out the current passing through the 5 volt source, isn't it? So what is current here? Current here is 6 divided by 3, or it becomes equal to 2 ampere. Here it is 1 ampere. Okay. So 2 ampere is flowing, 1 ampere is flowing, and it is flowing in the opposite direction. So the resultant current flowing through this arm will be equal to 1 ampere, or else you can go with the Kirchhoff's current law. So this is 2 amperes. This 2 amperes is equal to 1 plus 1. Okay. So the current flowing through this arm is 1 ampere, isn't it? The current in this portion is 2 amperes. And this 2 amperes is coming into this node. Now the 2 ampere is splitting into 1 ampere and 1 ampere. So the 1 ampere is the current that passes through the 5 volt source. So what is power? Power is V into I, or it is 5 into 1, which is equal to 5 watts. So what is our answer? Our answer is option A, which is 5 watts. So that is about question number 70. You can see that they will make the question look very unfamiliar. But the solution of the question will be extremely simple. Okay. So a normal candidate, when he is looking into this question, he will, at the first sight itself, he will think that this question is undoable, and he will just leave this question, because you has never seen a network shown as a circle with a network N1 and network N2. Okay. But you just need not bother about what is network N1 and network N2, and you just only focus yourself on these 3 branches, and this is the simplest answer. It is just 5 into 1, which will give you the result as 5, and you will get a 1 mark for GATE examination. So this is so simple. Okay. So most of the questions are logical. They are not actually mathematically tedious. Most of the questions are logical, and you have to put your mind into every question, like you try this question. Okay. So when you start trying the question will automatically unwind itself to a simple question. Now we are moving into 71, question number 71. They are making the question extremely lengthy, such that you will just look into this question and you will think like my time will be wasted reading this question, and you will just skip into the next question. The self-inductance of the primary winding of a single phase 50 Hz transformer is 800 millihenry, and that of the secondary winding is 600 millihenry. The mutual inductance between these two windings is 480 millihenry. The secondary winding of this transformer is short circuited, and the primary winding is connected to a 50 Hz single phase sinusoidal voltage source. The current flowing in both the windings is less than their respective rated currents. Obviously that will be so. The resistance of both windings can be neglected. In this condition, what is the effective inductance seen by the source? That is what is the question. So the self-inductance of the primary, you will have to read the question once or twice or thrice while before you start doing this question. I am doing this question because I already know this question. But since you are not familiar with this question, you will have to pause the video and read the question again and again and again, or you have to read the question from your workbook almost 2 to 3 times, and you must understand the question, what is being asked. Okay. So then only you start doing the problem. It will take some more time for you to prepare yourself. So the mutual inductance is given as 480 millihenry. So we are going to put these values into variables. So the self-inductance is 800. It is given as 800, 600, 480. So 800, 600 and 480. Okay. So this is the arrangement. Now what is asked? We want to find out in this condition what is the effective inductance seen by the source is what is the question. Effective inductance seen by the source. So we are going to make the inductance equation. So the inductance equation with respect to V2 is L2 di2 by dt plus M di1 divided by dt. So you have to write down this equation. Now the secondary is short circuited. Okay, secondary is short circuited. That means I2 is equal to I2. There is I2, but V2 is equal to 0. Since it is short circuited, V2 is equal to 0. So when V2 is equal to 0, everything becomes equal to 0. So L2 di2 by dt plus M di1 by dt goes to 0. So what happens is that we can equate this. Okay, L2 di2 by dt plus M or L2 di2 by dt is equal to minus m di1 by dt. So substituting the expression in terms of J and L, so j omega L2 I2 equals minus j omega m1. Okay, from this you can make an equation for I2 in terms of I1. So here j omega will cancel. So what is I2? I2 is equal to minus m I1 divided by L2, and you can see m and L2 and m is given, so you can substitute the values and I2 will be obtained as minus 4 divided by 5 I1. Similarly, equation for the first loop V1 can be made, and you can also substitute these values. So when you substitute these values, this expression will reduce to V1 by I1 form. You have to put the expression in V1 by I1 form because we want to find out the input impedance, isn't it? We want to find out the effective impedance. Effective inductance means it is effective impedance. So what is effective impedance? See, the machine is a transformer, so that means whatever effective impedance you see in the primary, it is actually the inductance of the machine. So you have to make it in the V1 divided by I1 form. So when you make it in V1 by I1 form, you will get it as j omega for 16 millihenry. So what is equivalent inductance? Equivalent inductance is 416 millihenry. Here you will have to substitute the value of I1. Okay, so we have obtained the value of I2 earlier, and you will have to substitute for I2 such that the expression reduces in terms of I1 only, and then you will be able to take I1 outside the bracket and you have to reduce it in the form of V1 divided by I1, and then you will get the equivalent inductance as 416 millihenry. Okay. Now going into the next problem, problem 72.